Hello again, and welcome to the fourth lesson on multithreading in C++. In this lesson, we'll dive a little deeper into the theory of multiprocessing to address a common question new learners ask. In our previous lesson, we explored how a software component called the scheduler prepares processes for execution by breaking them into smaller chunks of bytecode. Using a method called indexing, it then organizes these chunks by assigning each a time index to ensure efficient processing. Working closely with the scheduler is the dispatcher, which is responsible for sending these bytecode chunks to the CPU at the right moment following the assigned time index. Furthermore, we examined how the specific bytecode chunks sent by the dispatcher to the CPU can be illustrated in this table, helping us visualize the scheduling process in action. The seamless coordination between the scheduler and the dispatcher ensures smooth and efficient execution of multiple processes. However, in our example, we used 3 processes with a CPU that has 4 threads. But now, I would like to call additional processes such as Microsoft Excel, Messenger, and WhatsApp. As mentioned before, the scheduler will decide where each process is executed, assign it a unique parent thread ID, and break it into chunks of bytecode. The newly created chunks of bytecode are then added to the time index, making them ready for processing. Notice that while Apple Music and WhatsApp are executed on different CPU threads, Microsoft Word and Excel are sharing the same CPU thread 0, and the Safari browser and Messenger are sharing the same CPU thread 1. So the question you may ask here, how is it possible for multiple processes to share a single thread in the CPU? The answer to this question lies within the methodology of multiprocessing. Let's remember what multiprocessing does. In multiprocessing, processes never share the same memory and cannot open direct communication with each other. Each process is assigned a unique and constant parent thread ID that is never shared with other processes and is only known to it. Each process is divided into chunks of bytecode that are addressed using the same process's unique parent thread ID. The CPU thread ID, although shared between processes, is no more than a route to execute bytecodes. Using a method called indexing, chunks of bytecode from different processes are sent to the CPU at defined time points in an incremental time index. The interval between any 2 time points in the time index is determined by the time needed to process the associated chunk of bytecode, along with multiple other factors related to the scheduler algorithm, CPU, and other hardware specification. The time index intervals never overlap, ensuring that any chunk of bytecode is sent to the CPU after the previous chunk is fully sent. The perception that processes are running simultaneously or concurrently is due to the time index intervals being in nanoseconds. These considerations make the indexing table still valid. It also means that in multiprocessing environment, processes are fully independent from each other, and the CPU as a technology is merely a tool that is programmed very well to allow physical threads to be shared along different processes. The technique that allows a single CPU thread to switch between different processes is called context switching, which is fully owned by the operating system scheduler. Context switching adds a huge expense on the time index. This is why the CPU specifications play a significant role in helping to minimize these overheads. In fact, high-performance CPUs with more threads, along with other computer hardware and advanced scheduling algorithms, can handle context switching more efficiently, reducing the impact on processing time and improving overall system performance. Follow the link provided under this lesson if you want to learn more about the effect of the CPU and other computer hardware specifications on the performance of multiprocessing. Here is a summary of what you've learned today. Join me in the next lesson as we start talking about multithreading. But for now, thank you for watching, and I look forward to seeing you in the next video.